a quick intro. Jeanine loves languages. She spends a ton of time thinking about language design, pros and cons of different approaches, and particularly from a human-centric approach as well, which came to the design of Tulip, which is an untyped functional language Jeanine's been working on for I think like 2 or 3 years now, as well as a few smaller languages here and there, and also hosts emerging language discussion group called SNEC as well. So the talk today is about parsing from scratch with skeleton trees. And take it away, Jeanine. We're excited to have you.
Cool. So this talk is about skeletons, and it is in October. So I have my little spoopy skeleton ASCII art, which I hope you enjoy. This is where you can find me on the internet. I'll show this slide again later. Some of you also mentioned that you had been following the Tulip project. That is where you can find more info on Tulip. We have a website now. It's pretty fantastic. And this parsing approach is something that we're using for Tulip, and something that I sort of came across during research for Tulip, and kind of honed a little bit to that particular approach. Cool. So whenever I talk about parsing, there's a question that has to come up next, which is, what are we parsing? Because parsing is a really big field, right? You could be parsing protocols, you could be parsing gigabytes of C++ code, and all of these kind of require their own little approaches. So in particular, what I'm talking about is you're in an industry context, right? Trello is in particular in an industry context. And you have a language, you have some sort of text-based tool that you have to parse. There's a couple of constraints that come with this. One is that you have limited resources. You don't have, for example, a team of hundreds of open source contributors to fix your bugs for you or make your product more usable. And oftentimes your users tend to not be programmers. And I don't mean that they're not technical. Often these are, in the languages that I've built before, they were scientists or mathematicians or security professionals who knew a lot about their field and were willing to learn a tool, but weren't going to necessarily fix compiler bugs for me. So those are the constraints that we have that are a little bit different than sort of the generalized world of languages. But it gives us a couple of freedoms. One is we get to design our own syntax. We don't have to sit there and parse C++, which is a lot more difficult than what we have to do. And we get to control the environment. There was a language that I built a couple of years ago where I had to make a change to the syntax, but I had a database of all of the code that was ever written in that language where it was stored. And so I could just go make rewrite rules. So you have a very different kind of control over the environment if it's an internal thing than if you had kind of released it to the world. So this is sort of the context that I'm talking about parsing in. In different contexts, you might want to use different kinds of tools and approaches. I also use this approach for Tulip, and we'll get into why it was useful there. So what we're going to do today is first I'm going to talk about what parsing is and what in particular parsing is to us in this context in industry with those given limitations. We're going to talk about the solved problem of parsing and what the solutions are to the solved problem of parsing. I'm going to take a slight digression into what compilers look like and how we organize code in compilers and a couple of patterns. We're going to talk about skeleton trees. So we're going to build that up from our compiler pattern. So it'll take a little bit to get to exactly what skeleton trees are. I ask for your patience in that. By the time we get there, it'll sort of just naturally fall out. And then if we have time, we're going to go through an actual implementation sketch in CoffeeScript and talk about how it's not that hard. Cool. Everybody with me?
Sounds good.
Let's talk about what parsing is. If you go on Lambda the Ultimate, there is somebody who I did not cite here because it's not a particular particularly original idea, you'll find this concept of what parsing is, right? You take a stream of characters and you deduce if and how they conform to an underlying grammar. So, for example, if you have some kind of math expression here, some mini calculator language, you deduce two things. One is that this does conform to the grammar, right? And the second is how it conforms to the grammar with some kind of tree, right? And here we have, I've formatted this tree as an S expression with parentheses and the word saying what kind of nodes there. And of course, if you get text that doesn't conform, you just say, nope, it does not conform. It's a parse error. And with this kind of idea of parsing and what you're doing with parsing, you often end up with a situation where if you have a giant expression that has a little typo in it somewhere, all you say is parse error. And in an industry context, we need better than this. Remember, our users are not going to sit there and debug our compiler for us. We don't have hordes of open source developers to make our parsing better. So we need to take a slightly different approach in this context. Parsing for us is the front door to our tool, right? We're building a tool. It has a text interface. Parsing is the front door. It's where people start to interact with your tool. It is the UX to your syntax designs UI, right? You can think of it as the sort of implementation of the user interface for your text-based tool. It's the first way that the computer starts to understand what a human is saying. And we know this, but it's also a way for humans to kind of learn to speak computer, right? To learn to format text in a particular way so that the computer understands them in the way that they intend to. So for us, it's not good enough just to say whether or not it matches the grammar. We have to also say if the user makes mistakes, we have to give them a guide for fixing the mistakes, right? We have to say, at minimum, here's where the parse error happened. And the more context we can have at that moment where the parse error happens, the more information we can give them about how the computer was understanding it, and hopefully the model that we're using is similar to the way that the human is looking at the code and understanding, right? The point is to make this sort of communication connection between human and computer, right? So it's a very good goal in parsing to have your parsing model be very close to the way that a human is actually understanding the code. Because then you can kind of speak the same language a little bit. So we'll get to what that means a little more concretely later. So given that kind of perspective, let's talk about how we usually go about solving these problems. If you tell someone you're writing a language and you need a parser, and they tell you that it's a solved problem, almost all of the time they will tell you what they mean is that you should use some kind of eBNF-like grammar compiler. eBNF is extended Bacchus-Noir form, and it's, if you have worked with languages before, you are probably familiar with it. Otherwise, it's just a sort of specialized syntax to define a grammar. And it will compile it into a sort of platform-specific set of code that uses a particular kind of parsing strategy, like LAL or PackRat. And there's PEG parsers have become popular lately because they're a little bit simpler in some ways. And I note that it's academic, and I've used CKs here because it's often the case that using these kinds of tools, you don't necessarily know what all the research is that went into them, and you don't know whether the grammar compiler that you're using has taken into account sort of the latest parsing research. So you're kind of, it's a little bit of a black box, and you don't really know what you're getting. It can be deceptively easy. The marketing around these kinds of tools tends to tell you, oh, you just sort of write what you want, and then you always get the right answer. And they tend to only show you the happy case, where it parses successfully, and not, for example, what happens when your user has a typo. These kinds of tools, especially Lallar, were originally designed for NLP approaches, and in particular for English, which has a lot of infixity, right? A lot of things where you can't really tell the structure of something until you scan forward an arbitrary number of tokens and resolve precedence. So if you have a language that has arbitrary post hoc configurable infixity, this is probably an approach that you want to use. But remember, we're in a context where we get to design the syntax, right? And we get to, for example, say, we're going to limit what a user can use the syntax for. So we actually, 99% of the time, you don't need that. This is a good old Yagni, right? You don't actually need post hoc configurable infixity. In fact, I would say if you're designing a language for industry, you are 100% capable of making it LL1. LL1 means that you can sort of decide what kind of node that you're parsing with no backtracking. So you can scan from the left. So it's left look ahead 1. So you scan from the left, and you only need to see one token at a time to decide what you're doing. And they tend to not be optimized for error messages. And there is a lot of good research on these kinds of tools that make their error messages better. However, two things. One is a lot of the actual tools that you will find on your specific platform don't necessarily implement all of that. And because they're very platform specific, you can kind of get stuck with one particular tool. And the other is they're trying to solve a very general problem of error messages with arbitrary context-free grammars, for example. And they don't have the context of the particular semantics of the syntax that you have designed along with them. So they have to kind of give you error messages from a very abstract perspective, which is not necessarily how your users are understanding the code. And remember that we want our parser to understand the code in a similar way as our users do. Those are a couple of limitations with this approach. Another suggestion that you will often get is to just use a Lisp syntax, which is fine if that's what you want. There is no infixity in Lisp. You can parse it by hand really easily. But it really constrains your syntax design. And if you're okay with a Lisp, I guess that doesn't necessarily matter. But I would say, if you don't, whenever we talk about the UX of Lisp, people always suggest that you have to use a sort of higher level editing tool like paredit, or I think there's a new fancy one called parinfer. But your users, remember, we have non-technical users. We have non-programmer users. And they likely do not have that tooling set up. And finally, you actually, most of the time, want to parse things that are a little bit more than just forms and atoms. And so if you do it very naively, and more or less everything we do is going to be kind of naive because we don't have a whole lot of resources, you're just going to end up pushing what would be parse errors out to runtime to say, oh, we're going to define this special form for our particular site-specific semantics, and I guess it's malformed, right? But the S expression syntax can't necessarily enforce that on a syntax level. Another approach, and this is the one we're talking about today, is to use skeleton trees. And they kind of split the difference here. It's really easy to do skeleton trees by hand, so you can do them on any platform. In Tulip, we're bootstrapping using Lua with almost no libraries. So if you have something even more minimal than that, it's easy to do without any kind of external support. There are a lot fewer constraints on syntax design. You can have more or less an arbitrary syntax as long as it's LL1. And it's really great for macros. In fact, this approach was designed for the ability to have Lisp-style macros with not Lisp syntax. And of course, if you're just developing a text-based tool in an industry context, often you do not need macros. But this was actually very useful for Tulip. And I will go into that a little bit later. Okay, so to talk about what skeleton trees are, I'm going to first talk about what it looks like when we're writing a compiler and how we organize code in a compiler. So a compiler fundamentally is a linear pipeline from user input to some kind of interpretation, whether it's interpreting it by running code, by doing things, or by sort of creating host objects, or it's just interpreted in some way. The computer understands it. And we have this magic in the middle. And of course, it doesn't always get interpreted successfully, right? There's a bit of validation that happens in it. So validation gives us two things. One is the possibility that there's an error, and the other is a set of guarantees in the case that there isn't an error. So this is a basic concept of what a compiler is. And we can take this concept and apply a very powerful pattern to it called insert IR. And this is a programming pattern like any of your other programming patterns, but it's very specific to compilers. So IR stands for intermediate representation. And it basically says, I'm going to take this compiler and split it up into two compilers and compose them together. So a very common IR to use is an abstract syntax tree, right? A lot of people don't think of this as an IR because IR is more often used in backends of compilers. But it is an intermediate representation. And in a sense, we're splitting apart our compiler that goes from our input to some interpretation into a compiler that interprets your text as syntax for your language, and a compiler that interprets that syntax as some host concept. And with this, we insert the possibility of an error in the previous step. And from that error, we get guarantees in the case that there wasn't an error. So here we have said, we're going to validate that everything is correct syntax before we do anything else. And this is a really powerful way to split apart separate concerns. Another potential way, another IR you might insert here is some sort of compiled artifact. And you might do things like resolve symbols, do optimization passes, and you will add more guarantees. And you have another potential for an error here. And finally, you might use insert IR without actually creating another representation, but just for the guarantees. The perfect example of this is type checking, where you potentially use the same AST, but you have a guarantee after you go through the step that it is well typed because of the possibility of having a type error. So here we've taken a very simple linear pipeline and expanded it bit by bit by adding representations in between. And there's actually a compiler architecture that's becoming more popular now called micropass, where you take this to kind of an extreme where every single step just does one little thing and adds one little kind of guarantee. And you have a really long pipeline and you end up with something at the end with all of the guarantees composed. So when we're in a compiler, this is the primary way that we separate our concerns. It's a little bit different style of coding than, for example, writing a server or writing a front end, where instead of separating concerns by like creating libraries with interfaces, you separate concerns by creating new pipeline elements that communicate with each other through data and guarantees. So within one of these steps, you might see code that you would normally never write. You can, within one of these steps, you can lie, cheat, and steal to get one data format to the next. And it's okay because you've confined what the responsibilities of that part are and what the guarantees that it's supposed to provide are. And the abstraction lines are drawn through the data that is passed between. So if you see some code that you normally wouldn't write, it's okay as long as you have these data boundaries drawn. Cool? That's the compiler pattern I wanted to talk about. All right, so this is a talk about parsing. So we're just going to look at the parser, which is just sort of a little mini compiler that ends at the syntax representation. And for the sake of what we're talking about, I'm going to design a little mini syntax here. This is actually Tulip syntax. And at the bottom, we see the tree that we're going for, right? We want this to parse into, okay, it's a module and it's got two assignments, one of x to a 1 and one of y to a 2. Cool. So at the end of the day, we're going to have this very nice data structure that tells our backend exactly what kinds of things that we have in sort of site-specific semantic objects. And you can just throw an EBNF or EBNF-like parser at this problem, and it will give that to you. But fundamentally, what it's going to do is it's going to understand this this code by proceeding through it character at a time. And so when it comes to across an error, unless you've done some fancy custom coding, all of the context it has is, I expected these characters, but I have this character, right? So there's a very common, widely used IR that's inserted here between your text input and your AST. Does anybody know what that might be?
I do.
Yes.
It's a lexical stream, so you tokenize it.
Yes. Okay. Cool. So yes, you break it up into bits, and this makes our error messages better because we've separated, for example, the comment handling into the first part, and we are now starting to understand this stream a little bit more like a human would, right? A human doesn't go through this character by character. They look at it and say, "Oh, here are the bits of it," and now I understand what it is, right? That at module isn't 7 characters, it's 1 word, right? So we make our little stream of tokens. A token is just a name and an optional value, which is a string. And that's fine. And then we can throw that at our some kind of grammar compiler, and it will it'll give us this data structure back. And that grammar compiler can now be a lot simpler. It doesn't have to, for example, handle whitespace or comments or any of that gunk, which you would otherwise have to handle. So that's fine. But there's actually one more step that we can add here. There's a weirdness about this token stream that is a little bit different than how a human understands it. Does anybody have any idea what that might be? An IR to insert between tokens and the AST. I'll give you a hint. There's something that should bother you about this token stream. And the thing that should bother you has to do with this LBRAC token. Nobody? Okay. So in a sense, when you look at this code, and let's look at it without all of the angle brackets. When you look at this code, a human will actually see one sort of semantic line, right? It's a module, foo, and then a thing in square brackets, right? And of course, they also see the square bracket token and then the closed square bracket token. But in a sense, there's a thing with three things in it here, right? The keyword module, the name foo, and a thing in square brackets, right? And inside those square brackets, there's two things, right? There's this assignment and that assignment. And this is, in a sense, this tree tells you that, but it's a little bit overly specific. It tells you that this is this particular semantic concept in our language. So there's an RIO that we can insert, and it is called a skeleton tree, where all you say is, here's how it's nested, and here's how the syntax is broken up into groups. And so I've used parentheses here to show you what the kind of nesting that we're talking about is. So here we have one kind of item that has three things in it. It's a module. It's the keyword module, the name foo, and a thing in square brackets. And inside that thing in square brackets, there are two things, right? The first line and the second line. So in this data structure down here, we see a tree with three kinds of nodes. One is toke, which just contains a token. Another is nest, which is a nested set of skeleton trees with an open and closed delimiter. So we keep track of those tokens for later. And then we say item, which is the same as nest, but without delimiter. So it's a sort of grouping that doesn't necessarily have delimiters around it. The lexical stream has no guarantees and no restrictions on the nesting of the delimiters that we have. It also has no restrictions on how we handle, for example, new lines, how we separate things without delimiters. In order to get to a skeleton tree, we have to be well nested. So now we have added the guarantee that everything is well nested before we even start building up our AST. We've also encoded this particular semantics of how new lines work in this tree. And we haven't said that this is a module. We haven't said that these are assignments, right? You can still get a successful syntax tree if you leave out an equal sign, right? We just said, here's how it breaks into pieces. Cool. So some advantages of this is, first of all, when you're trying to make this into this data structure here, you can actually just use naive splits and do extremely naive coding at this point, because you've already done the recursion. The recursion has already been handled in the skeleton tree parser. So when you look at x equals 1, 1 could actually be an arbitrary parenthesized expression, and you would still see one thing, right? So you can get there and just say split on equals sign extremely naively. Which you would completely not be able to do from the token stream, because you could have arbitrarily nested things with arbitrary tokens in them. They give you cheap macros. There's a paper here that I suggest that you look up and read if you want to read more. It's not called dexpers, but that's a search term for if you want to find it. Because if you look at this data structure and kind of tilt your head and squint a little bit, it looks kind of like an S expression, doesn't it? Right, an S expression has two kinds of nodes. One of them is an atom, and the other is a form, which is a parenthesized form. And here we have a token, which is kind of like an atom, and a nest, which is kind of like a form. An item is actually the same as nest, just without delimiters. So you can take these and for the price of potentially adding a quote kind of node and a couple other things, but all similar things that you would have to do in Lisp, you can get macros. You can get exactly Lisp style macros. You can have these, and you can have these reified in the runtime. And that's exactly what Tulip does. And this approach was developed for the Dylan programming language for exactly that reason. Dylan is a language that does not use Lisp syntax, but has Lisp style macros using exactly this approach. And one of the reasons it's so good is that the guarantees that it gives you is exactly the limitations that you want to have on macros with exactly the freedoms you want. A macro should be able to use any token in any way that it wants in ways that the parent language doesn't necessarily support, but it has to be well nested, right? We have to be able to easily tell where the macro invocation ends so that we can wrap up the macro invocation and call it. So cheap macros. This is completely trivial to do by hand. You have probably given an interview question to a candidate to do something very similar to this. You just wrap up your list of tokens into a nested tree structure, right? It's a pretty straightforward recursion problem. So you can do it by hand. You are not dependent on any frameworks, and you can control the error handling yourself, which means that when you give error messages, you can speak the same language as your user. For example, when you're doing this part, when you're doing skeleton to AST, and this is left out, right? Instead of saying, oh, I hit a new line when I didn't expect a new line, right? We hit the end of the expression and we see a new line and we were expecting to see an equal sign. We get to say, oh, here's this item that you were trying to define. Here's where it is in the source. Here is the stuff that's around it. And I didn't see an equal sign in there, so I don't know what you meant by that specific thing. Rather than, I was trying to do this whole parse and something bad happened right here, right? You have a data structure that represents the syntax as your user understands it. So you have more context for errors. Cool. Everybody with me so far? That's what skeleton trees are. Go on.
I was just cheering emphatically. I'm with you.
Oh, cool. So how are we doing on time? We got about 20 minutes, so we can go pretty quickly through this implementation. I've done this in CoffeeScript. I was told that this shop uses CoffeeScript for a bunch of things, and CoffeeScript is nice and easy to fit on slides. So it's good. Okay, so to dive into the implementation, first we're going to make a lexer by hand, and then we're going to make the skeleton tree parser. In order to make the lexer, we're going to depend on a class called scanner, and I'm not going to show the implementation of this class, partly because it's pretty trivial and partly because there's actually at least 4 or 5 libraries on NPM that do something very similar. A scanner is a stateful object that scans through a string. It has a string backend and a position within the string. And it can take regexes and test whether that regex matches at that particular position and move the position forward, right? So we can just send regexes at it and test whether they match. I've added setup and teardown because there are some situations where for example, other languages where you might need to do some I/O handling. You might be doing this off of a file stream or something, and you might need setup and cleanup functionality. Scan is sort of the core method that you use. You give it a regex. If it matches, it returns the match and remembers what the match was. If it doesn't, it returns null. has a current location, and it not only keeps track of the index within the string, but also the line and column numbers. So every time we do a scan, we check how many new lines were in it and update our line and column numbers appropriately. We can ask it for at the end. That's pretty simple. And then it'll remember the last thing it matched. So we can ask it for the last string, the string of the last match. We can get match groups. And we can get the last range, which will be a pair of location objects, one of which represents the beginning of the token, and one of which represents the beginning of the scan, and the other represents the end of the scan. And finally, skip is the same as scan, except that it doesn't update the last match. So we can just, it only moves the location forward. Are we good with the scanner? It's relatively straightforward. You could implement it by hand. Cool. Oh, and for this implementation, we're using regular expressions. It is completely possible to do this in a land where you do not have regular expressions. In Tulip, we're using, again, Lua with no libraries to bootstrap this, and we have no regular expressions, and it's fine. We just go character at a time and check whether the character is the thing. Because most of the regex that we're using can be replaced with very simple while loops. Okay, so Elixir is a lazy stream of tokens, as was mentioned. You can use a generator or as you like. I tend to do it this way, in the sort of naive generator way, in the way that you do generators in languages that don't have generators, which is just an object with setup, next, and teardown methods. So we'll call setup, and then we'll keep calling next until we get an EOF token, and then we'll call teardown. Cool. I'm going to add one more method to this Elixir called getLast. So we're going to remember exactly which token we last yielded. So every time we call next, we're going to store the thing that we return in state.last. And then we have this little helper that says, make us a token with the last range of the scanner. So an important note here is that tokens do not only have a name and a value, but also have the range on them. So the token itself carries the source location with it. And what we want to do is we want to push that source location as far along the compiler pipeline as possible, into the runtime if you can afford it. Because anytime something can go wrong, you want to be able to point back to, here's the place in the code that you need to look at. So we never, ever, ever throw away source location data if we can avoid it. So tokens always have their source location, both start and end, so you can highlight it if you like. And we keep track of all this stuff. So let's zoom in on, oh, sorry. First of all, we're going to have a couple helper methods, skip whitespace and skip lines. Skip whitespace is just going to say skip some whitespace. Skip lines manages semicolons, new lines, and comments, which in Tulip syntax, for example, are all the same, all mean a new line. And we skip the whitespace around it using this while loop. So if we see a new line, we skip it and then skip the whitespace. And importantly, we always queue ourselves up with all of the whitespace skipped before we return the token. So that whenever next is called, we are already queued up to where we expect the next thing to be. So in particular in setup, we call skip lines so that we are queued up to the place where the first thing is going to start, because we don't care about new lines at the beginning. Okay, so let's zoom in on this next method where all the magic happens. So we're going to store whatever we do in state.last, so it's available for us. The first case is if we're at the very end of the stream, we give back an EOF token. Pretty straightforward. And then we just have this giant if-else chain. And if this makes you uncomfortable, I would say don't worry about it. I've seen people try to take this if-else chain that always happens in a lexer and break it out into some kind of DSL, some kind of framework, and it always goes badly every time. The best way to code a lexer is as if you were writing Fortran, right? Just make it a big else if chain, right? Like, it's the most flexible. It's the easiest to modify later, and you've already reduced the complexity of what you're doing by making the lexer only do what it's there to do and leaving the rest to other steps, right? We've isolated it through insert IR. Cool. So after we scan, if we see a new line, then we have a new line token, and we skip lines. So multiple new lines is the same as one new line. If we see an open square bracket, we skip lines because we actually don't care about new lines after our square bracket, right? We just queue it up to the first thing in the square bracket. And we give an LBRAC token. And if we see a closed square bracket, we only skip whitespace, because after a closed square bracket, you might see a new line that ends the current item, right? This is a pretty common pattern where you skip lines after the opening delimiter and skip whitespace after the closing one. And then we have some tokens with values that use scanner last match and scanner last group. So for names, we have our regex that says what a valid name is, and for keywords, it's got an @ and then a valid name. And we use last group to grab the value. So that's pretty straightforward. And at the very end, what I like to do is just say, okay, I don't know what we're looking at, so I'm just going to move the string forward one character and yield an error token. And that error token is going to be handled later. And this way you get sort of the maximum number of errors. You don't just find the first error and stop. You get to say, here are all of the things wrong with this text, right, that we couldn't parse, which is extremely valuable for a user. And you could do a little bit of squirrely coding to make sure that you don't do that more than one character in a row. But I didn't have space on the slide to do that. So we didn't expect this character at this particular location. So that's the whole lexer. Like I said, it's actually not that complicated. It's got a giant if-else-if chain, but that's kind of what you're doing. There's actually not a whole lot of fundamental complexity here. Most of the code here is actually what you're doing, and actually specifies the semantics of what you're trying to encode in this step. So once you've got your lexer, once you've got your stream of tokens, we can make it into a skeleton tree. This is going to be a pretty naive recursive descent parser. So we start by doing the setup on the lexer, and at the end we tear it down. At the very root of our syntax, we have items. And I've introduced a new skeleton tree node called root, which is only at the root that just contains items. And we parse items, and we're expecting the EOF token at the end. And there is no opening delimiter. And we're going to have a couple of helper methods, parse term and parse paren, and these are going to be co-recursive. So parse term is sort of the base. We're going to start by looking at this at the very base case, the else case, where we just say it's a token. Here it is. It's a token node, right? It's just a thing that we see. If we see an L-paren, we're going to say, okay, grab all of the terms that you see, and then give us a nested thing. And this is a feature that exists in Tulip. But you notice we're handling L-paren differently than L-brace and L-brac, because we actually want to ignore new lines inside of parentheses, so that you can pretty print things without them being. You can pretty print things in parentheses without them being broken up by new lines. So we handle that specially. And I put that in here to show that if you have sort of custom squirrely things, you can actually just do them because you're coding it by hand. LBrace and LBRAC have items in them, so we parse items. Matching here would just be a map that takes LBrace to RBrace and LBRAC to RBRAC. And we return your skeleton tree. If we see one of those error tokens that we made before, we're going to say that there was an error, and otherwise we have our token. Parse items is a little bit more difficult because we have to do the new line splitting. So we maintain this sort of the list of the items that we've parsed and the current elements of the item that we're parsing. And flush just says, is a helper function that says we're done with the particular, with the current item that we're parsing, wrap it up in an item and push it onto the items list. So the main body of this is a loop. We're going to loop until we see the matching close delimiter. So we see the matching close delimiter, we're going to say flush the last item and return the list of items that we've parsed. Cool. If we see a new line, we flush the current item. If we see an EOF, that's an error because we're looking for a closed delimiter. And if you remember, we used a parse items at the very root, but we were expecting an EOF, so that would be captured here. So by the time we get down here, we know that that an EOF means an unmatched delimiter. And here, when we have the error, we have the open token. We did a couple squirrely things to have to pass the open token through this method, but it's worth it, right? This angers me about Ruby all the time. It'll say, I got to the end of the file and I was expecting an end token and not tell you where the opening token is that it was expecting the end to. So it's very important. Pass your context through. When there's an error, make sure you have all the context that you need. If you see any other kind of closing delimiter, that's an error, right? We can't make a skeleton tree with mismatched delimiters. And otherwise, we parse a term and push it onto the current thing, right? That's very simple. And parse paren is sort of the same thing except simplified in that we only care about terms and we only care about our parens to close the thing. So if we're parsing inside of a parenthesis and we see an RBRAC or an RBrace, that's an error. Otherwise, we push the thing. And that's literally it. That is all the code. There is no more code. That will get you a skeleton tree. And from there, you recurse to the skeleton tree and parse your skeleton tree into your semantic AST. And that is an exercise for the user. But again, you can use naive splits and very kind of naive coding strategies to do that. So your takeaways today, first is skeleton trees are not that hard. They're just an instance of a very common compiler pattern that we already use all the time. Parsing is also not that hard if you limit in fixity and limit yourself to LL1, which you can do. Error messages are really important, and if you have to do some squirrely roundabout coding to get them to be good, it is worth it. One thing that I forgot to mention is that most of the actual open source production level languages that are used out there that use eBNF-like compilers almost invariably have a giant pile of hacks on top of it that somebody implemented like years later because the error messages were bad from the parser. And we don't have time to do a giant pile of hacks on top of a drop-in solution. So we just have to be a little bit careful about passing the context to ourselves so we know what is what. Your parser is your UX. It is very important for your users to be able to get their jobs done. You should be used to pipeline thinking for compilers and not worrying too much about messy code necessarily inside of one step, as long as the architecture is good. and to be skeptical of frameworks. Frameworks are good. They make things pretty easy, but they often lose you context that you could use to make lives better for your users. And finally, and most importantly, skeleton trees are cool, and now you know a cool thing. And if you want to read more, I would search the internet for DXpers, short for Dylan Expers, and you will find the paper that I mentioned that builds up the same kind of strategy but justifies it a little bit more through the macro side and how you would use this strategy to have Lisp style macros in not Lisp syntax. So that is all that I have, and I think we have about 5 minutes for questions.